All right, line A6, we're going to take a look at learning task 3, which is going to be rectified circuit calculations. And I want us to be very clear about what's going to happen inside of these calculations. There's a lot of math that is laid out on top of the module over here. They're going to give us a bunch of new formulas to go and put together. But ultimately, what is happening is we're going to go and take AC that we normally have. We're normally going to go and have a load connected across our AC like that. And now what we are going to do is we're just going to put in a block over here that is going to become a rectifier. And what a rectifier is going to do is it's going to go and take this AC sine wave that we had on this side, and then it is going to go and create a rectified DC on the other side over here. Okay, we're not showing the guts, it's all the diodes, so we just took a look at that. But what it's going to do is it's going to go and take the same amount of voltage that we had on this side over here, if it's a full wave, and it's going to go and flip that over and drive it through here. Instead of by current going whoosh through in this direction and whoosh through in that direction, what we're now doing is we're taking the current and we're going to go and drive it through whoosh in this direction, whoosh in this direction as well. Which means that really what we're going to go and see in a full wave rectified circuit is we are going to go and see the same amount of power that is going to be put out. Just all of that power is going to be in one direction over here. You remember how when we had an AC resistive load, we saw that we always had a positive amount of power because I'd get a positive voltage and a positive current and then a negative voltage and a negative current, right? This is all the way back in your line A1 and A4 at the very beginning of the year. This now over here, we're going to get positive power as well because our voltage is going to go and develop a current that's going to go and be in phase with it, right? If we got resistive over here, which means that ultimately I'm going to go and get the same power waveform as what I would get if I had a regular AC type of circuit. So what we're going to see when we rectify is that we are going to go and have power, the same sort of RMS power that we are going to go and have off of it. The power is going to stay the same. Remember how much of a fan I am of power, because power doesn't trip you up as much, right? That's when we do full wave rectification. When we do half wave rectification, we're going to take this AC input, and instead of rectifying both sides, we're actually going to go and lose one of those sides. And when we lose that voltage, we lose that current, and we lose that power as well. And so what we should see from this is that we're only going to go and get half the power that is going to be out of a half-wave rectified type of circuit. A lot of the way that this module is laid out makes it seem complex because we're going through the math of it. We're still going to go through the math of it. We need to go through the math of it. But you cannot lose sight of the fact that, look, if I'm going to go and rectify AC, full wave rectification, I'm going to go and get the same power out as if I had a regular AC circuit. And if I half-wave rectify it, I'm going to go and get half the power out as if I had a regular AC circuit. So these ones that we're going to look at now, the formulas, are just going to go and give us values that we can pull out of it. But this whole concept of, that we're either going to get the same power out or half the power out is really going to help us inside of calculations. Practical calculations in the real world. Okay, so we had a bunch of formulas that were given to us that all dealt off of the maximum value of voltage, the peak value of voltage that we were going to deal with. We've looked at instantaneous values of voltage, so starting at the very beginning there, we know that E instantaneous is going to be my Emax times my sine of my angle, whatever I'm going to go and take it at. So I can figure out any sort of a value along that AC sine wave by taking the sine of that angle and knowing what that peak is, and then I can calculate exactly what that point is over there. We've also got our RMS, which is our root mean squared. What was the purpose of RMS? The purpose of RMS was going to go and give us the cross compatibility, right? We wanted to have a value of voltage that we could say, hey, this is my RMS value, this is my DC value for flatline DC. Remember we said we wanted to have a voltage that if I had a flatline DC would give me a certain amount of power and that I would be able to see the same amount of power from an RMS value. So it was an easy conversion. It's our most common one that we are going to go and use. And then we are going to go and have what is called our average value of voltage. And the average value of voltage, we ignored that earlier this year because we said, hey, we're going to deal with it when we get to rectifiers. Well, the time of reckoning has come. We must deal with the average value of voltage. And the average value of voltage is going to be a DC value of voltage that we are going to have. It is going to tell us what a DC meter would read. DC meters read voltage and current differently than AC meters. So we have to have different types of calculations to be able to go and find these things. Let's start with this drawing that we have over here. Average values that we are going to go and have. If I've got a full wave rectifier circuit, I'm going to go and take what I had here before. I'm going to go and flip that one to the top side through the magic of the diodes. And then that is going to go and allow me to get a fairly high average value of voltage. My average value of voltage is always going to come off of the max. You'll see that in all of our calculations. We take it to the max, and then we figure out what we've got for an average. It is going to be Emax times 0.637. This 0.637 simply is going to go and be 2 over top of pi that we have. We just call it 0.637. It's kind of our standard name that we have for that thing. Our standard name. It's a standard calculation that we have, but it's going to be 2 over top of pi. If I go to a half-wave rectifier circuit would have had a full AC like that, but then instead of flipping this over, we just cut it off like that. Which means that we're now going to go and take my maximum value and we're going to divide it in half. Take a look. 318 is half of 0.637 that we are going to have over here. So my average value is going to go and drop, right? We no longer get to average out that entire piece. This piece now becomes a value of 0. So we drop that thing. So we end up with this Emax times 0.318. You can go and take a look at that value over there, and that would become 1 over top of pi that we would have. Remember that pi talks about, the number of radians we have in a circle. We haven't talked much about radians this year. We said we've got a bunch of formulas that incorporate radians. You remember the XL and the XC formulas? Those had 2 pi, which meant that we were looking over top of 2 halves of the circle. Now at this point, we're going to be looking at, 2 halves of the circle we're going to be looking at compared with 1 half of the circle that we were looking at. Once again, not super critical for us to know, or to understand this whole radians thing. We can just accept it. We can utilize the formulas as they've been, scientifically proven and given to us. And as long as you remember, these numbers, the 0.318 and the 0.637, which by the way are on your ITA formula sheet, you should be good to go for these. Do note that the average is what a DC meter would read. It is not what the waveform underneath is. This is just a DC meter, because it cannot understand sine waves, takes all of these sine wave shenanigans and it's like, I think we call that 0.637 of whatever that max is. It spits out a DC value. Same with this one over here. RMS values also still exist. RMS stands for root mean square, and it's our way that we go and develop power, equivalent power for flatline DC compared to AC sine waves. RMS values are going to be the same. Take a look at this. For me to have a full wave rectified circuit over here, I would say that my RMS value is my max times 0.707. This is the exact same formula as what we say RMS value would be for a AC, right? Max times 0.707 gets me the same one. So I get the same RMS power out of a full wave rectified circuit. Anytime that I am going to go and have a half wave rectified circuit, I'm going to get a different formula out of it. And my new RMS, my new power type of voltage that I'm going to utilize is going to be my maximum times 0.5. Now some of you are like, well, what the heck are we doing with RMS in a DC? Because these are both DC, right? They don't cross the axes. The reason that we need to use RMS values is because this shape over here. We have to use that in order to go and calculate the actual area that's underneath the curve, and that actual area underneath the curve is going to allow us to calculate the amount of power. Now, we don't do that at a granular mathematical level. We just do that by plugging in our actual values that we are given. But that is why we need to use RMS still inside of this DC type of waveform, so we can get the true actual power. Remember that what we talked about, all that we're doing is we are taking if this is going to be full wave, we are going to go and take all of the voltage, put it over top, and as a result of that, all of the current is going to go and follow that, if we're talking about full wave here, and therefore all of our power is going to go and look like that. That is the exact same power that I would have out of a circuit compared to if I had a circuit that was going to be AC. I don't know if you remember this from the AC. We'll just draw it here. If I got volts, I'm going to have in-phase current and in-phase current. And then if I multiply a positive times a positive, I get a power. Looks like that. And then here I multiply a negative current times a negative voltage, and I get a power that's going to look like that. Poorly drawn because I'm no artist, but you see that it's the exact same power waveform across from one side to the other. Going back to where we are here. So as far as our load is concerned, I want you to highlight that sentence at the top of the full wave circuit. As far as the load is concerned, a full wave rectifier simply changes the direction of the AC. Instead of it going swish, swish back and forth, it's just going swoosh, swoosh, both through in the same direction. So we are going to go and utilize that. The half wave, we are only going to go and get 50% of the power. Because we only get 50% of the waveform, we're only going to deal with 50% power. Let's start with the circuits. Now, before we do any calculations that we're going to follow through, what I want to do is I want to go and add in one more circuit. Because what we're going to see over here is we're going to go and see a couple of layouts of the exact same circuit. So hold on a second here. Let me just add in one more slide here. Take this one here, and we'll start by removing that one over there. And we're going to start with just a straight up AC circuit. Because sometimes rectification seems overly complicated. We forget that at the guts of it, we're just changing the direction of our current. I'm going to go and take 120 volts. This is RMS because it's got no subscript on it. And I'm going to go and place it over top of 12 ohms that I'm going to go and have over here. When I do that, I'm going to go and develop power. I'm going to go and develop current as well. Let's calculate those values for this as a straight up AC type of circuit, and then we'll go and make that conversion into our full wave rectified circuit, and then we'll take it down into a half wave rectified circuit as well. All right, let's start with the current. What's our formula? I is equal to E over top of R. So if I take my value of volts, how many volts? It must be, according to Kirchhoff's law of voltage, dropping all of them across here. So 120 volts over top of my value of resistance, 12 ohms, that I'm going to go and have over there. I'm going to go and develop a value of current that is going to be 10 amps. So 10 amps that would be flowing through here. We know that we've got 120 volts that would be dropped across it. And I know that I would be taking that 10 amps out of this source over here. What's my amount of power that I'm going to go and have off of it? Well, my amount of power is going to be E squared over top of R, or I times E, right? My volts times my current. Let's do the volts times the current. That's relatively easy. 10 times 120 volts would get me to a value of 1200 watts. 1200 watts. I times E equals watts. So we got 1200 watts. 1200 watts that's going to be delivered out of this circuit. How's it going to be delivered? Well, it's going to be delivered out as heat that's going to come off of this thing. And where's that power come from? It's coming from here, right? So it's going to be 1200 watts that's going to be supplied by this. Beautiful. So we've got 1200 watts in, 1200 watts out. The circuit balances. We see all of our volts that we have on the input side that are being dropped across our load side. Over here, we see we got the same current, 10 amps through the source, 10 amps through my load over here. Let's just draw out at the very end here now what my power and voltage and current waveforms look like. So I'm going to go and draw out a voltage waveform. We'll make the voltage waveform this red one. Okay. And if I've got my voltage, when I've got 0 volts over top of 12 ohms, I would have 0 amps of current. So I'd have 0 over there. When I get peak voltage over top of my resistance, I would get peak current. So I'm going to have a peak over there. When I get 0, once again, 0 volts over top of my 12 ohms, I would get 0 amps. So I've just, made a couple dots. Now I can play connect the dots. I learned this back in kindergarten. I'm still really good at it. So I'm just going to play connect the dots, and we'll just, do the same for that one. I see that my current is going to be seen as being in phase with my voltage. In phase meaning it's crossing the x-axis in the same direction, doing the same thing at the same time. There's our x-axis, that gray line that we just drew in. Last thing that we would develop off of this would become my power. So if I have got 0 volts, 0 amps, I'm going to have 0 watts over there. If I have got maximum volts, maximum amps, I'm going to go and have maximum power over there. And over here, I'm going to go and have 0 volts, 0 amps, so I'm going to have 0 power again. Over here, I'm going to have a negative maximum current times a negative maximum voltage, but a negative times a negative gives me a positive, so I'm going to have a dot up there again. And here I've got a 0 and a 0, so I'm going to have a dot down there. Once again, connect the dots. We end up with this power waveform that's going to look like this. Something along those lines. There's far better illustrations of it in your modules. Go back and find them if you don't remember exactly how it looks. But, if you're happy with this, let's work with it. Okay, that would be this thing as a straight up AC type of circuit. Now, what we're going to do is we are going to go and change our circuit into DC. Why are we changing it into DC? Well, for the sake of a resistor, we wouldn't do it. For a lot of our other loads, we absolutely would. Electrochemical processing is a huge area where we need to go and have DC, so we can go and create chemical recombinations or chemical strippings, where we can go and change stuff. So we do need to have DC. Let's take a look at a full wave rectified DC over here. Ultimately, what are we going to do? I'm going to go and just draw a little split down the inside over here. And I'm going to go and say, look, this side over here, we got AC values. This side over here, we are going to go and have DC values. I know that this side has got an AC input waveform that's going to look like that. I know that this side over here is going to go and have a DC waveform that's going to go and look, oh man, that's a terrible looking one. Try that again. I have a DC waveform that's going to go and look like that over there. Ultimately, do I pass all of this waveform through to my load on this side? Absolutely I do. I just pass it all, so it's going to be inside of the same direction that I'm going to go and have over here. So how then do I go and make my calculations? Well, once again, when we take a look at all of our formulas reference the peak. It is always that we're kind of following through on this, where we're going to go and take RMS values, and then we're going to go and take them to the peak, and then we're going to go and take them back down. When we're dealing with power, we are going to go and take them back down to RMS values on this side. And then my RMS values on that side we can use to develop our total amount of power, etc., that we are going to have. Once I know my total amount of power on this side, I would know my total amount of power that I would be delivering on this side over here, which would mean that I could then go and figure out my VA in, VA out, all the rest of that stuff. Those same rules, the amount of power that's going to be dissipated by a circuit has to be supplied by a circuit, are the exact same as on a transformer. They're not as formalized, but we get that. The amount of power supplied by our source has to be the same as that dissipated by our loads. All right, let's start with our RMS value. We'll take it up to a peak over here, and then we're going to go and take it back down to an RMS value. We know that if I go and take my ERMS divided by 0.707, it's going to get me to a peak value. So take 120 divided by 0.707, and we're going to go and kick up to our peak. So 20 divided by 0.707 gets me to a value of 169.73. We usually call this thing 170 volts. And for most of our calculations, we're going to be fine with just calling it 170 volts. We're cheesing out on our calculations as is because we're not even treating our diodes as having a voltage drop of 0.70 volt. Technically speaking, we should be dropping 0.7 on one of these, 0.7 on the other one that's conducting, which would mean that we would be down by 1.4 volts. But because we're looking at this from a power electrician, not from a electronics technician standpoint, it's a small enough voltage drop that we can effectively ignore it inside of what we're doing here. So we've taken this thing up to a peak value of 169.7 that we are going to go and have. How do we go from a peak down to a full wave rectified? Well, we know that if we go back up to, this one over here, my RMS value is going to be my maximum times 0.707. So I'm just going to go and reverse that calculation, take that 169.7 and multiply by 0.707. Gets me back to a value of 120 RMS on this side. It is an RMS rectified value over here, but it still has an RMS type of value to it. RMS does not mean AC only, it just means a voltage value derived off of a sine wave. So do we have sine waves here? Yeah, we got sine waves. We just split and flipped them over here. So I'm going to go and have an RMS value of 120 volts RMS over here. If I have got 120 volts RMS on this side, I can go and figure out my power by using any one of my regular power formulas, because RMS is always used to develop power. Do I use my average to develop the power? Absolutely not. Could I? Yeah, I could do some conversions from average, take it to peak values, etc., and then get that down to a watts value, but why would I take myself through a bunch of steps that I could screw up when instead I could just jump straight into my RMS and go to that, not lying to me, power thing? I'm going to go and do that. I'm going to say that power is equal to E squared over top of R. How many volts am I putting over this? 120 volts RMS. What's my value of resistance? 12 over here. So I can go and say 120 squared divided by 12 is going to go and give me my power. 20 squared divided by 12 gets me to 1200 watts that I'm going to go and have. So I see that this load over here is going to be dissipating 1200 watts. Hold on a second. Before we go further on our calculations, I just want to go back to this over here. How many watts were we dissipating over here? For that same 12 ohm resistor fed from 120 volts, we see 1200 watts over here that we're going to be dissipating. What have we done on this circuit over here? We've just taken all of our AC and flipped it so that it's all going through. But note that it's all that we put in is still all being driven through here. We're just driving it through in one direction alone. So we get the same amount of power that we are going to go and have over here. It's a beautiful, beautiful thing. Now, let's figure out what these ammeters inside of here are going to be reading. Well, our ammeters are going to be based upon what side they're in. What is this one looking at? This is an AC side. What is this one at? This is a DC side that's going to be over here. Same with this voltmeter. What is this voltmeter? This is going to be a DC reading. Anytime that I say DC, in my mind, that equivalates to an average reading that we need to be taking. DC is going to be an average reading that we need to be taking for that one. AC over here is going to be an AC RMS type of reading that I'm going to have. How many watts am I delivering out? 1200 watts. Therefore, how many watts must I be taking in a power on this side of the circuit? Well, I have to be taking that in, all of it, right? So it's going to be 1200 watts over here as well. So my source over here is drawing a grand total of 1200 watts that we are going to go and have. We can take that watts that we have over here, put it on this side over here, and then just divide out our value of volts to figure out what we have for our value of current that we are going to go and have on it. Let's do that. Watts divided by I is equal to E that we are going to go and have. 1200 divided by, not divided by I, let's do divide by E because we're looking for I. Watts divided by E is equal to I. 1200, that's going to be my watts, divided by 120, that's going to be my E. It's an RMS value because we're working with power, we have to be working with RMS. Therefore, we can go and say 1200 divided by $1.20 gets me to an AC value of 10 amps. Let's place that over here. 10 amps that we are going to have through there. Do I need a subscript on it? Absolutely not. Why not? Because it is an RMS type of value, and we don't subscript those. We can, but it's not necessary. Cool. We got that side done. All right, this side over here, how do we get DC values out? Well, we need to get DC values out by going and converting to DC average. That's going to be these ones over here. Now that circuit is going to be a full wave rectified, so I'm going to have to go from my peak and multiply it by my 0.637. So I'm going to start by figuring out my value of voltage. Once I know my value of voltage, then I'm going to be able to go and take that value of voltage and use that to go and figure out a value of current using Ohm's law. We'll start with this one now as being 169.7. It's my E max, right? So we'll start by writing this formula out. V average is equal to V peak times 0.637. My peak was 169.7. So we will multiply that 0.637. Gets me out to a value of 108.09. This is going to be a DC average reading. Remember that DC voltmeter, DC ammeter will read differently. They've just got different guts inside of those meters because they're just tuned to, look for different things. So a DC voltmeter on here is going to go and read that 108.09. That's going to be my voltage over here. So let's place that in. 108.1 volts that we are going to go and have there. If I know that value of DC voltage over top of resistance, I can go and calculate the DC current that I would have as well. I is equal to E divided by R. So I can go and take my DC voltage, 108.1, divided by my resistance. Resistance does not have average DC or any other types of, things. Resistance is R is equal to K times L over top of CMA, right? We know that this is going to be a constant based upon the physical build, so we don't need to worry about using, RMS or average or any other types, of AC or DC. It's just resistance is resistance. So this has got a resistance of 12 ohms. So I'm going to place that inside of there. So I can go 108.1 divided by 12 ohms. Gets me to a current of 9.008. We will round that one to 9 amps that I'm going to have over here. So my DC is going to be reading 9 amps over here. Okay, going back through this, once again, the important things to do on this one is identify what I'm reading. This is going to be AC. This is going to be DC. This is going to be DC. Once I know what I'm going to be reading, AC or DC, then I say, what units do I use? If this is going to be AC, then I'm going to go and work with RMS. Right? That's the general unit that we are going to work with. So I identify that as RMS. This is DC. It's rectified DC. Therefore, I would be working with average values. This is DC. It's rectified DC. Therefore, I would be working with average values that you would have for these. There's a couple different methods to calculate power. They do give you a formula before that says, power can be my maximum voltage times my maximum current divided by 2 for a full wave rectified circuit. And that would go and give me 1200 watts. Or it says, look, power can be my RMS, voltage times my RMS value of currents, which we calculate inside of here, which would get us the 1200 watts. Or power can be any one of our power formulas. Which one did we use? We used E squared over top of R, using RMS values, because that's what we do with those types of formulas. We got to that 1200 watts, and we saw that it's the same 1200 watts as what we had when this thing was just a straight up AC circuit. We get the same power out when we go to full wave rectification. Okay, really important to understand that if it's a resistive circuit, and we're only dealing resistive over here, we're not dealing with anything with power factors, but if I go full wave rectified, I'm going to get the exact same power out of a full wave rectified circuit as I would out of this straight AC one. Let's take a look at our half wave rectified circuit over here. On a half wave rectified circuit, we're going to go and have our AC sine wave that we're going to feed in. But then on this side, we're going to go and chop off half. Okay, so we're going to be ghosting half of our AC. We're going to be leaving that at a value of 0 volts for that part of the cycle over there. So that means that if I take a look at it, I'm going to go and still get normal operation here and then nothing inside of here. This is going to be calculable. We can go and calculate by doing the same path as what we did before, which is going to be RMS, take it to a peak, take it back down to an RMS, and then calculate our power. Preferable to go this route because, once again, power does not lie, or it's not as easy for us to go and screw up, basically. Let's take our value of RMS, take it to a peak. 120 volts that we have over here. If we take that to a peak, we just did this one on the previous one, but we'll divide by 0.707, which is going to go and take us from 120 volts up to a peak of 169.7. Then we're going to take it down to RMS. But what type of a circuit is this? Only a single diode that's inside of here. Therefore, this thing is going to be a half-wave rectified circuit, and we need to be using this formula that we have over here. My ERMS for a half-wave rectified is my max times 0.5. Let's do that over here. My maximum, 169.7, times 0.5. 169.7 times 0.5. Oh, that's a 0.8. Delete that, 0.5. Beautiful. Gets me to 84.85 volts RMS. So we're going to put that into there. 84.85 volts RMS on this side. Okay, that 85.85 volts RMS is an RMS type, which means that we can now go and use our same formulas that we've had before to go and calculate. We've got a value of resistance here, we've got a value of voltage, so we can go and calculate value of power. Power is equal to my E squared divided by R that I'm going to go and have. So we'll take this value, RMS value, because it's power, we're working with RMS. Have to work with RMS when we're working with power. So E squared, we're going to divide that by my R. My R is going to be just 12 ohms because resistance doesn't have RMS or average units, so we'll put 12 ohms underneath there. Punch that in. So we get 84.85. We'll say squared divided by 12 equals a value of 599.96. We'll do some rounding. We'll take this thing straight to 600, but you should see that 599.96 is going to be 600 watts that we are going to go and have here. Beautiful. Let's place that in there. 600 watts that we will have. What do we know about this voltage? Well, we know that on this side here, when we rectify this, that we are going to go and have, at this point where we've got 0 volts, over top of that resistance, we're going to go and have 0 amps of current. So 0 volts, 0 amps. Then when I get peak voltage, I'm going to get peak current, then I'm going to get 0 volts, and I'm going to get 0 amps as a result of that. And then over here, I'm going to have 0 volts, I'm going to have 0 amps, and over here, I'm going to have 0 volts, I'm going to have 0 amps, etc. So I can go and once again play connect the dots, and I see that I'm going to get a current waveform that's going to look like that, and then it's going to go in flat line along that axis. Which means that if I take a look at my volts times my amps, I've got amps and volts. Over here, they're going to be at a value of 0. Over here, they're both going to be at a peak, so I multiply those together to form a peak. Over here, they're back to 0, and once again, we play connect the dots, and we see that we get that power waveform. But now we only get half of it. Remember that before on our previous circuits, we had a power waveform that looks like that there? Now we have chopped that all up. Because we get no volts, we get no amps. If we have no volts and amps together, we get no power together. So we're losing half of our power. Really, that's what's happening inside of here. Let's just erase that because we've lost that half there. What does this mean? Well, take a look at the value that we just calculated. 600 watts over here. Compare that to what we had when we were full wave. There we had 1200 watts, right? So now we're saying when we're half wave rectified, we only get half the power out. When we compare that to our AC circuit over here, we saw that we had 1200 watts. We saw that when we did full wave rectification, we got the same amount of watts out. And we saw that when we went to half wave, now we're only going to go get half the watts that are going to come out of this thing. What's my value of volts going to go and be? Well, my value of volts, let's start by identifying our type of voltmeter that we have here. This is going to be DC, right? That's what we have on this side, is DC. So it's going to have to be DC volts, which means that DC volts are termed in average, AVG. My average value for DC volts on a half-wave rectified circuit, that's going to be this one over here, is going to be my max times 0.318. See that max that we have up there, 169.7? We are going to go multiply that by 0.318. Gets me to a value of 53.96 volts. This is going to be a DC average value of volts. So let's place that in there. I think I'm going to just round this one. 53.96, we are going to round that to 54 volts. So we're going to go and say 54 volts AVG, average value of volts. We do want to subscript it because we are looking at a average value. We need to know what we are looking at over here. If I have got an average value of volts, I can also figure out an average value of amps if I wanted to with a DC ammeter, right? If this was on this side, that means it's going to be halfway rectified. We move from AC on that side to DC on this side, so it would have to be an average. And I would have to do that using my average value of voltage. So if I wanted to go and get my DC amps over here, I would just go and say I is equal to E over top of R, right? Use my DC values, 54, divided by my resistance, which is going to be 12 because resistance stays the same. And you do your 54 divided by 12 gets you to 4.5 amps. So this would be 4.5 amps average. It's a DC value that we're seeing off of that one. Okay, that is going to go and be my DCs that I'm going to go and have. What am I going to go and have on my ACs over here? On my AC, this is where it gets a little bit tricky on here. And really it's just going to be off of the amount of resistance that I'm going to go and have that is going to be, calculable on this side. Now, what we want to do, this is what the incorrect route is going to be, okay? And we're just going to start by writing bad, okay? The bad way to do this would be say, well, I've got 600 watts on this side, so I can go and take that 600 watts over to this side and say that, I is equal to my watts divided by my volts that I'm going to go and have. And if I would do that, I should come out to an I that would become what we would see as being 5 amps. Right? 600 divided by 120 would give us an incorrect thing of 5. 600 divided by V. Now some of you are like, what? Watts can lie to us? No, the watts are not lying to us. We're just forgetting about something. How does this formula work? This formula works off of the fact that it's going to be an RMS value of voltage that's happening for both cycles. When we rectify, when we're blocking here, is there any current that is flowing? Absolutely not. So that means that this current that we would have over here would not be actually like that, because this formula on this side would be us assuming that we're going to get the complete waveform that is being passed through, and therefore we're going to have some current on this side, we're going to go and have some current on that side. That's not what's happening. Right now, what's happening is we're getting current only on this alternation, and we're getting nothing that's happening through there. That's why this is a bad formula. Because what we're trying to do is we're trying to go and relate the watts on this side to volts on this side. And the watts on this side only happen for half the time, right? And the volts happen all the time. So what can we relate? Go back to what we just drew over here. Current and then no current. Why don't we relate it through current? Then we can use our power formulas and it's going to go and be correct. So here's my current that I'm going to go and have through here. What's my power formulas? We know that power is equal to I squared R, right? That's going to be our formula that relates current and resistance to my power that we're going to have. We can use that same amount of resistance that we have over there because we know that that amount of resistance stays the same. It's not RMS or average or anything like that. So I'm going to go and rework this formula. We'll divide R over to this side, and then we'll take the square root of both sides, and that would isolate I on the one side. We end up with this formula that states that I is equal to my power divided by my resistance and the square root of that. That's just a rework of that formula over there. So we can go and take our values. I know it looks like 12, which is handy in this case, but it's supposed to be an R over there. We can take our values of power, 600, put it over top of my 12, and then we can go and take the square root of that. When we do that, it's going to bring us to a current of 7.07 amps that I'm going to have. Okay? What we are relating through is we're relating the current because the current is the one thing that does actually pass through the circuit. Remember, we're blocking half the voltage. This way, we're relating all the current that we're putting through, the hump of current and then the line of current. We're relating that on this side. That's why it works over here. Okay, the last section is going to go and deal with something that's going to be referred to as form factor. And form factor just compares AC to DC. And it is always going to go and follow this one layout. Let me just go and grab one more here. Let me just duplicate this one here, drag that one here. I'm just going to get myself a blank slide over here. Okay, form factor only works with resistive loads. You need to know that. This only works when we're dealing with resistances. So as soon as we have a power factor that is going to be on our load side, then we would have to go and include that. So we're only going to go and work with resistive loads inside of here because we're still just, at the elementary stages of our electrical theory. This is only second here. You've still got third and fourth where we can overly complicate things. So we'll start with this thing here. Form factor, often referred to as just FF. You'll see FF on stuff. FF is going to be my RMS values over top of my average values. And for a full wave rectified circuit, my RMS is going to go and be 0.707. My average is going to be 0.637, so it's going to be a 1.11. So FF, FW, full wave, is going to go and be 1.11. And my form factor for my half wave is going to go and be 2.22. They go through the permutations, how they get those values inside of the book there. Basically, they're just canceling out the Emaxes on both sides and doing the 0.707 over 0.637 and then the 0.707 over 3.18. Gets me those form factors that we're going to have over there. What we use form factor for is when we know that we have got a circuit and we have got a rectifier and we want to know values from one side over to the other side. Here's the first example. They're going to go and say we got a single phase bridge rectifier. What is that? That's going to be full wave that we would be talking about. So we've got bridge rectifier. Say that's a BR over there. And they're saying, look, we're going to go and use a bridge rectifier because we need full wave DC. And we need that full wave DC to be a value of 12 volts. On this side over here, what value of AC must I be putting into this thing? Well, it's going to be 1.1. And if I take a look, if I am looking, I've got my average value over here. That's what's given us, 12 volts. That's going to be my DC, right? So we identify that as being average. And what am I looking for? I'm looking for my RMS value that I'm going to have on my input side. So I'm going to go and take this formula. I'm going to multiply the average over to that side. And so it's going to form me this new formula that's going to say RMS is equal to my average times form factor over here. So I could take that 12 volts, multiply by 1.11, and it's going to go and get me to an average value that I would need to have of approximately 13 volts. That 13 volts, by the way, would be with a lossless bridge rectifier. In reality, how many volts should we expect to drop out of a bridge rectifier? Close to, 1.5 to 2, because each of my diodes, and we're always passing through 2 diodes, would give me a voltage drop of 0.7. So I would take that 13 plus, another 1.4 would get me to a value of about 15 in practicality. I'm not going to go and ask you to calculate in the diode drops when we are doing this in our actual calculations for the exam. But you should just be aware of that. Just if you're looking up other additional things online, sometimes they're going to include diode drops. Depends on whether it's for electronic or electrical that they're looking at things. Electronic engineers are going to have to start calculating that. We're just looking at kind of the course values here as electricians, so we can understand how they work. All right, they're going to give us another one. They say that we have now got a half-wave rectifier. So we're going to go and once again just draw this as a block diagram over here. We're going to say, whoa, where did that go? Oh, no. Okay, 1 second. I got to pull that back. All right, we're back, but completely lost all that. Crashes out of me once in a while. Highly frustrating when you're trying to draw stuff through, but it's what it is. We'll go back to what we were just talking about, though. We were just trying to work our way through the last calculation side of here, which was going to be a half-wave rectifier over here. And that half-wave rectifier, they're telling us that we're feeding into that half-wave rectifier with 53 volts. Now, if we're feeding in, that must be on my RMS side, right? And we're looking to go and get what my output is going to go and be. Remember that my form factor is going to be my RMS divided by my average, right? We're looking for average, so we need to isolate that. So we're going to go and multiply average up to the top. We're going to multiply form factor down to the bottom. So we do that cross-multiplying thing, which gives us RMS over top of form factor is equal to my average, like that. So now we can take that RMS value that we have, 53, and divide it by my form factor. What type of form factor is it for half wave? It is going to be a 2.22 that we are going to go and need for that one. So we are going to take 53 volts divided by 2.2, and that is going to go and tell us that we are going to get out approximately 24 volts. It works out to become 23.87, but close enough that we can go around that thing. We'll call that thing a 24 volt. In practicality, once again, should be not 1.4, it should be 0.7 of a volt smaller, because in halfway we're going through a single diode, which is going to maintain a constant drop on it. Okay, that is all of our form factor and AC to DC conversions that we are going to go and have. The self-test for this one is complex. We've got a multitude of different types of conversions that we're going to have. We see biphase, we see full wave, we see half wave, all of that is going to be inside of there. If there's watt meters, go through it. it is going to go and give you a workout on how to calculate these values.